Hello, organic students. I am trying this new technology to try to capture my lectures. And this is going to be about a 4-minute and some effort on my part here. But I'll be emailing you this stuff. And you'll have this email-wise from Blackboard. And we'll be talking in Chapter 8 about aromaticity and electronic effects. And I have here the two classic calculase structures of benzene. And that double-headed arrow is not an equilibrium arrow. There's no equilibrium between the two species. These two structures, neither one of which adequately represents benzene in all of its properties, and I apologize for my poor drawing. These structures don't really fully adequately explain the properties of benzene. And now, these are the line structures, and these are what you'll be seeing from now on. I just put in the carbons and hydrogens above just to show you, where they are and to remind you that they're there. But neither one of these calculase structures explains the experimentally observed properties of benzene, which we've been observing for over 150 years. Benzene is stable to hydrogenation relative to an alkene. I mean, here is an alkene, and never mind. The alkene, you can see ethene is hydrogenated nicely over palladium at reasonable temperatures and pressures to give ethane, but benzene just laughs at hydrogen and palladium. There is no reaction. That must mean benzene is pretty gosh darn stable, which it is. You can also see that benzene has an increased stability to electrophiles relative to alkenes. And I can show you that with these two examples that I pulled out of my head. You can see ethene smoothly brominating in carbon tetrachloride. Carbon tetrachloride is a solvent to give 1,2-dibromoethane, otherwise known as ethylene dibromide, I believe. However, excuse me, I'm allergic to benzene. Benzene here, when treated with bromine and carbon tetrachloride, there's absolutely no reaction. Nothing at all at room temperature. The red color of the bromine is not discharged. Hydrogen bromide gas reacts with ethene to give ethyl bromide. However, in the case of benzene, there's no reaction. And there's also combustion data that I'd like you to read about. That is, benzene just doesn't seem to give off as much heat per mole as, say, three separate three separate ethene molecules would do. So, in fact, one of the classic tests for benzene was it would burn with a very, very smoky flame, which indicates there's incomplete combustion, which indicates the heat of that combustion is not very high. That is, benzene burns, but stubbornly, but it does burn. I was present at Syracuse University in 1989 when one of my friends had a benzene still catch fire, and just took one drop of benzene on the heating mantle and the whole thing went up. And it burns with a very smoky flame, and they emptied I don't know how many fire extinguishers. Finally, they had to call in the Syracuse Fire Department, and there was a lot of soot and things like that just from one still. So it does burn, but it's nasty. The increased stability of benzene is due to the delocalization of the pi bond electrons. And I think the one thing that indicates that delocalization is that all carbon-carbon bonds in benzene are the same length. We know that by X-ray diffraction. And if you look at page 322, figure 8.1, they draw a much nicer picture of the overlapping p orbitals than I want to attempt here. If benzene were alternating double and single bonds, the bonds would be different lengths. The double bonds would be shorter than the single bonds. That is not the case by experiment. So, benzene has a lot of delocalization. Now, in section 8.3, which begins on page 322, you should understand the difference between a resonance contributor, a resonance structure, also known as a contributing resonance structure, and a resonance hybrid, which is the actual structure of the species. The resonance hybrid is a composite, if you will, of the resonance contributors. And not all resonance contributors contribute equally. It's just like me when I go out with friends and we all split the bill. I don't contribute very much because I'm cheap. And some resonance contributors, and we'll talk about that in my next lecture, are not as good as others because there's too much separation of charge, or you'll put, for instance, a negative charge on a more electropositive, that is less electronegative atom, and so forth. Now you'll be asked to write resonance structures, that is the single structures, not the resonance hybrid. And please see section 8.4 on how to draw those resonance contributors, and there'll be a homework on that coming up at some juncture, and that's on page 323 to 326. Those rules, they walk you through some examples. As your text states, the greater the predicted stability of a resonance contributor, the more it contributes to the structure of the resonance hybrid. And some resonance contributors are very, very minor because they're not very stable. The more a resonance contributor contributes to the structure of the hybrid, the more similar the contributor is to the real molecular species. And there are examples, pages 327 to 328, examples 1 through 5. And that's all I have for you right now.